Hello everyone. Welcome to our lecture 10 in the unit Mechanics of Solids. In this lecture, we will learn some knowledge on the generalized Hooke's law and combined loadings and also some thin wall versions. So in the last lecture, we have learned how to transform at a point in a component. As we know in lecture 1, so any load may result in strain. Okay, then for most material, Hooke's law will be applied. So of course, for this way, we still can, as we learned from last lecture, we can transform the stress. So that's why similar way we can also transform the strain. Okay, in the structure at any point. Of course, there are so many types of the loading conditions, as I mentioned in lecture 1. So whether torsion, normal stress, bending, there's so many of this. And also in the previous lecture, we have studied all of the different topics of these things. So that's why for this lecture, we will learn the knowledge, how we can transform the strain by using generalized Hooke's law. Of course, with this lecture, we'll also cover a lot of things, for example, for thin wall pressure versus, and also we can also learn how we can use the knowledge before we combine all the loading conditions, okay, for the real problem. Of course, this part, we will only give some basic knowledge, okay, but next lecture, so we will combine all things together. So you will see how complicated it will be. But remember, last part just give you the knowledge of the real industry problem. So as we mentioned and also announced in the related announcement on the final exam, okay? So this lecture is the last part for the final exam, okay? So that's why this is very important for you to realize some problems. So of course, in this lecture, we'll give you some knowledge on the absolute maximum shear stress via Morse circle, because last lecture we only mentioned it for the maximum in plane, okay, shear stress. But now we will learn how we understand for maximum, so absolute maximum shear stress via Morse circle, and also the absolute maximum shear stress for plane stress conditions. That will be used for a lot of real applications. But that's still very easy, not hard, okay? So that's why we will give you some general knowledge. And then we can understand for generalized Hooke's law and also some strain transformation. But after this lecture, so we will determine the absolute maximum shear stress, determine the shear stress developed in thin wall pressure versus. This mostly will be used for the final exam, but the easy question, okay? But let you know a little bit later on. So determine the stress developed in members, cross-section, wing, axial load, torsion, bending, and shear occurs simultaneously. But this part, I said, is quite complicated. So if there's some question in the exam, that's a very simple way. They'll give you a hard question, okay? But in a real problem in industry, that's a lot of things, much more complicated as we test the examination, okay? So that's why next lecture will also further expand this kind of thing to tell you the real problems, how complicated it will be. But all the basic thing will come all together. Okay? Okay. So in the last lecture, we have learned to construct Morse circle to work out, okay, a lot of things. For example, we can determine principal stress, sigma 1, sigma 2, and then the angle. Okay, maximum shear in plane shear stress, and also in any location, so arbitrarily, so inclined angle, we can work on all the stress and so the normal stress and the shear stress in any location. So by using the Morse circle. But remember, Morse circle is widely used in real problem in industry. Okay, so that's why this knowledge must be tested in the exam. Okay, but remember, you must get the idea how to work all these things. So of course we can recap how we can use these things. So of course we can get anything, get the state of a plane stress in XY plane. It's quite simple, okay? So of course we can work on normal stress, we can work on shear stress by using another thing for use a method of section, as we mentioned in lecture 3. And also later on for the normal stress for bending, everything we can work on. Eventually we can work on this thing. So as I mentioned in last tutorial, we also use real problem how we can solve these things. But basically, when we try to get anything, we must pay the special attention on the right hand this plane. So we should find where is sigma x, where is sigma y, where is tau xy. So of course you should know the sign convention for all these things. So that's why we should know how to work on these things. So after we know these things, so now we should locate the center of this circle, because we should draw the, or say we can construct the coordination. Okay, sigma, that's a stress from left to right hand side. Okay, so that's where we become positive. And shear stress will be from up to down. That means downward will be positive. So after we construct this kind of coordination system, then we should find the center of the circle. The center of the circle is the sigma average 0. That means that will be 8, the center on the average normal stress. So then we can see this value. Later on, we can find the local reference point A. That's a sigma x tau xy. So from this one, we can get a point of the anything here. Of course, that's the distance between CA will be the radius of the circle. So of course, from school level, we should know how we can get this kind of distance. So from sigma x minus sigma average square plus sigma tau xy minus 0 square. Okay, or use this equation as we mentioned before. Okay, use this equation. You can, the answer will be the same. Okay, so that's from here, so we can get the radius and we can draw the circle. From the circle, we can, of course, we can work on the principal stress. Okay, so of course we can say normal stress will be sigma 1, sigma 2. Sigma 1, of course, will sigma average plus r. Sigma 2 will sigma average minus r. So from here we can get all the things. And of course, the maximum in-plane shear stress will be from this average. From the average, just draw these things will be 90 degrees. Okay, but remember this 90 degrees not just the 90, but we must from the sigma x to xy at the point A for reference. We see the angle will be counterclockwise will positive. So now of course you should find which one is which one. But for this thing, we must care about the signs and directions. As we say, the positive shears on more circle is downward, and the positive angles is counterclockwise. So that's why we should know which one is which one. So if you still cannot remember, please go back to our lecture and then tutorial question. You can get the point. As I said, this will be the examiner question in the final exam. Okay, because the key knowledge in industry and is widely used in industry. Okay, so of course we can say this is the absolute value. Let's say it's an in-plan, okay? But actually, when we come to all the things, as we mentioned, you will use the method of section. We'll always try to get where's the maximum shear stress, okay? But remember, we just say maxima or maximum in-plane shear stress, but not necessarily there's a maximum value. So that's why from here, since the stress of a ductile material depends on its ability to resist shear stress, it becomes important to find the absolute maximum shear stress in the material when it is subject to a load. That means this in-plane shear stress will be not always the maximum absolute maximum shear stress. Okay, that's why from this way, we must get the idea how we can get these things. Okay, as we mentioned before, for a state of a plane shear stress xy, so they only resist the one is sigma x, another one sigma y, and also tau xy, only 3 components. But for other things, so sigma z or tau xj to tau yz will be all 0. Okay? So that's why for this thing, there's only have this thing. That means we can only have a sigma x, sigma y, tau xy. We come to plane. Okay, use a plane these things. Use the Mohr circle. That means only have a sigma 1, sigma 2 for this situation. Because we can work on sigma 1, sigma 2. We want to find out where's the maximum value. So of course, sigma 1, sigma 2 are two components. So there's only two things. Either sigma 1, sigma 2, or both positive, or both negative, or one positive, one negative. That means they have two situations. One is both with the same sign or have opposite sign. So same sign, that means positive, so tension, tension, or negative, compression, compression. Or opposite, one tension, one compression. But remember, sigma 1 must be greater than sigma 2. So that means sigma 1 could be positive and sigma 2 could be negative. Okay, for the opposite sign. That's why we can have, say, sigma 1 and sigma 2 with the same sign, or sigma 1 and sigma 2 with the opposite sign for these two situations. So then we'll see what's happened for this kind of thing, whether this is absolute maximum value or not. So now we learn how to get anything of this. We still use a Mohr circle to get this information. Because we say if this is in the XY plane, okay, that's for most cases. That means we can only move sigma 1 and sigma 2. So from the XY plane. But XZ plane and YZ plane, that means we should also include to see what's happened. Because the in plane 1 not always may be out plane. Okay? So from here, if sigma 1, sigma 2 have the same sign, so that means both are positive or both are negative. So for example, we see this situation. So therefore, this kind of situation, we can see how we can observe these things. So that means this one XY plane like this way, sigma 1, sigma 2. But we observe for XZ plane. So that means this sigma 2 will be out of or inside, okay, or into the plane. So that means here, for X plane, we only see sigma 1. And the same way for YZ plane, we can only see sigma 2. Okay, that's reasonable, yeah? So from different view. That's why from this kind of case, we can work out the circle, for Mohr circle, for different planes. For example, for this one, for XY plane, like this way. So that's a similar way, because sigma 1, sigma 2. So like this way. So either positive or negative. For this kind of case, both positive. Okay? So from positive, that's why we can see sigma average with center and the circle is D. And of course, again, XZ plane, this means half of sigma 1. Okay? Then, of course, the XZ plane will be circle of half this sigma 1. And then, of course, YZ plane, you can see YZ plane, this one from the 0 to sigma 2. That's why we can see draw this circle. So, of course, based on this situation, if you still can remember, so the maxima in plane shear stress will be at the average value, okay, of this thing. So the sigma average. So then we can see the relative to the value here. This is the maxima in plane shear stress for XY plane. Same way, we can work on in maxima in plane shear stress for YZ plane. Same way, we can work on the maxima shear stress for XZ plane. So which value will be here? This is a circle for XZ plane, the circles with the maxima radius. So that's why for here, the absolute maximum value will be on the XZ plane, not on the XY plane. Everyone clear? Okay. So that's why from here, we can see this one, the maximum shear stress is located on the XZ plane, not on the XY plane. So that means out of the XY plane. So that's why from here, we can get this value. So tau absolute maximum value will be half of sigma 1 with the radius of this. So now, of course, that's what I say here. The absolute maximum shear stress is an out of plane shear stress. The absolute maximum value is on the xz plane rather on the xy plane. So that means the absolute value will not equal to the maximum in plane shear stress on the xy plane. So that situation will be different. Of course, we can get this idea. So if on the same plane, okay, it's on the same side, so sigma, sigma 2 on both on positive or both on negative. So that means the maximum shear stress will be out of the shear plane. So not on xy, but it will be on xz plane. On the other side, we will do the same way. So it's about if they have opposite sides, so you can see last value will be xy will be sigma 1 plus sigma 2 half center. But remember, so the maximum value will be roughly the half of sigma 1 minus sigma 2. So we can get this value so very easily, okay, but use the Mohr circle. Same way for xz plane and the yz plane, you will see their radius will be much smaller. So that means if they have a different sign, so sigma 1 in tension, sigma 2 in compression. So now, of course, we can see the absolute maximum shear stress will be on the xy plane. That means will be same as the maximum in plane shear stress. So that's the situation we can see. So for this kind of case, we must work on sigma 1, sigma 2, whether have the same sign or with a different sign. So then, of course, the absolute value will be different. So that's why we summarize for here on these slides. If they have the same sign, that means the absolute maximum shear stress will be half of the sigma 1. If this one will be opposite signs, that means the absolute maximum shear stress will be half of sigma 1 minus sigma 2. Okay, that's the way we can work out. Okay, we see one example, how we can get this idea. So for example, example 1, due to an applied loading, an element, okay, at the point on a machine shaft, this is a bit common, for example, for cars. So everything will be there, okay? Is subject to the state of a plane stress, show like this way. So determine the principal stresses and the absolute maximum shear stress. So if we just count here, determine the principal shear stress at the point, that's the same as in the last lecture and the tutorial, quite simple, yeah? So that's why we can work together. Okay, I want everyone engaged to find where's the values. Okay, that's very important for you. You can construct the Mohr circle. Okay, so I can see here. This one shown here, we can work on if we want to construct the Mohr circle, must know sigma y, sigma x, tau xy. Okay, so we work together. How much of sigma x? Negative 20 megapascal, yeah? Why? Why negative? Because complete, yes, good. How much of sigma y? 0, because nothing shown here, yeah? How much of tau xy? Negative 40, why? We look on the right hand side, yeah? Because the downwards, that means here is negative. If you know this thing, then almost you get some mark here. Okay, so that's why from here you can get some knowledge. So then we can say, hey, from here we can see sigma x, sigma y, tau xy. You get a mark. Then we should work on the center of the circle. When you want to work on the center of the circle, we should work on the average normal stress. So sigma average will be half of sigma x plus sigma y. Clear? So then, because negative 20 plus 0 is negative 10 megapascal. That means center will be negative 10, 0. When you come to here, you will get a mark, 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 mark. Okay? So that's why you can get this thing. Then later on, because of the circle, we should do these things. Then we should find the reference point. Okay, the reference point is a sigma x tau xy for the coordination. Okay, that means you should write down the reference point A, -20, -40, because sigma x tau xy. Clear? Then we'll work on the distance of AC, this is a radius. You either can use the way is we mentioned in the lecture, half sigma x minus sigma y square plus tau xy square and the square root. Okay, or you can use the way we use another way. You can work on the distance between A and C. Oh, sorry, A and C. Yes. So that's about from here, sigma x minus point in the center. Okay, so that means we can see the xa minus xc square plus ya minus yc. Okay, that means here minus 40 minus 0 square. We can get these things. Or I said you can use this equation or plot it. That's the way it can work out. So that means from here you get a radius, you will still get a mark. Okay, then you draw the circle, you will get a mark. Okay, so that's why from here, after we get this thing, then we'll work on sigma x, sigma 2. Sigma x, of course, is on the right hand side. Clear? So that means sigma y is sigma average plus r. So sigma average here, -10 plus r here, 41.23 megapascal. Then you can work on 31.23 megapascal here. Same way, we'll work on sigma 2. So that's a sigma average minus r. So that's where we can -10 minus 41.23, and you can get the value. So you will get a mark. Similar way, yeah? Then we should put the angle. So that's why you see the reference of the A. So remember, because the counterclockwise will be positive value. Sometimes from this way, you can see this one is easy for your work, but this one relative to the sigma 2. That's why here we can work on the sigma P2. Okay, for the principle for the number 2. So that's why from here we can work out the distance here. So that's why from here you can see the tangent to theta P2 will equal to this value minus divided by this value. This value is a tau xy. This one we should work out. So that's with from the sigma average minus sigma x. Okay, that's why from here we get the thing. So you can use your calculator, you can work out. But remember, there's 2 times of sigma P2. So that means here we can see sigma P2 should be 37.98 degrees. Then we can get this value, draw these things. Okay, that's why we can find the angles. So of course, based on this one, we can work on the first step. You get it's easy way for your workout. Yeah. But next one, we should work on the question, the absolute shear stress. Clear? Absolute shear stress, we need to work on sigma 1, sigma 2. Sigma 1 is 31.23 megapascal. Sigma 2 with negative 51.23 megapascals. So whether it's positive or negative. Sigma 1, sigma 2 have opposite signs. Everyone clear? One positive, one negative. So it's opposite. So we can come back here. If this is opposite, so that means tau absolute max will be half of sigma 1 minus sigma 2. If this is the same sign, it will be half sigma 1. Everyone clear? So, okay, because we know this is the opposite sign. So then we can see this stress have opposite signs. Then we'll see tau absolute maximum value will be half of sigma 1 minus sigma 2. Sigma 1 will work out, sigma 2 will work out. We'll put all the thing with a 41.2 megapascal. Clear? So of course, the sigma average will be half of this value. So we can get a negative 10 megapascal of these things. So that's why for here, we can get the values easily. So just a little bit more, clear? So that's why these things we should keep ourselves on the pin, okay? But the first step, remember, you should know where is sigma x, which one is sigma y, which one is tau xy. For first step, please don't make it wrong. Anyone clear? Easy, yeah? So that's why for this, if you put it in exam questions, do it. You will get it very easily. Just follow step by step. Okay? Not that hard, yeah? Just find out sigma x, sigma y, tau xy. Get the average value, get the center, get the radius, get it done. Draw the circle. You can get it very easily. So not that hard, yeah? Okay, good. So of course, we will try to get anything for xy plane. But still sometimes we will know, hey, this is for xy plane. Well, put this one as xy plane for this. But actually, sometimes you will know, we'll put everything here, we put this here, but like this will change. Okay, there are band or anything, you can do many things. Because as we mentioned before, there's many things will be changed because you have a bending, you have a torsion, there's so many will be communicated. So that's why for these things, we still should care about, as we mentioned, for plane stress, there's only with the two normal stress, sigma x, sigma y, and one shear stress, tau xy. That's it. For other components will be zero. Okay, that's why we know this thing. But remember, for real case, this thing is quite a simple way. And also, most of the case will be like this way. Okay, but still there's one way. There's not only thing will happen on xy plane. Still sometimes they will change because of different situation. They will go to much more complicated situation. So that's why from this way, where we go a further complicated thing because the sigma z will not zero. Tau xz will not be zero. Tau yz will not be zero. So definitely situation will be much more complicated. For this situation, we'll call Chua-Axial stress condition. For this kind of situation, will be more complicated. But how can get this point? How can understand what's happened will happen? For example, we push these things down, they will go down. Okay, we put it in tension, they will stretch. So, but we cannot see. That's because they're still within elastic deformation. But in their case, how we can see, how predict the values? So of course, we can use the principal superposition. We can work out. As we mentioned, principle of superposition is quite useful in industry. Yeah, you can put many things together. You can put a torsion, bending. There's so many come together. Or just individual work out a thing and summarize. Okay, we can say this could be okay, sum up or subtract. So you can see all the values. Okay, so that's why we can see from here. This value could be from, say, we could be x, y, z change. Okay, but then of course we can see this could be work with because of normal stress. Could also be shear stress. Could also have a bending. Could also have other things, notation, so many other things. Okay, so that's why for this thing we can sum up all the things from the situation. For example, you will see work on sigma x, sigma 2, sigma 3. So 1, 2, 3, or sigma x, sigma y, sigma z. Of course, every normal stress will induce the strain or change of the shapes or dimensions. For example, here we can work out, say, sigma x, sigma y, z for every location. For example, sigma x, of course, usually will put a tension or compression. But remember, x and y and z will also produce such kind of way. So that's why we can put all the things together. Why? Because we learn from lecture 1, there's a proportional ratio. Proportional ratio is is equal to negative strain lateral divided by strain axial. So of course, the strain lateral will be equal to minus nu times epsilon axial. So of course, we can get something like that. So negative nu sigma axial over E. E is Young's modulus. So this is from lecture 1. Okay? But we come here, of course, because of so many things come together. So sigma x, of course, this one in tension or compression, so normal stress. That's why this one will use Hooke's law. Okay? Sigma x over E. But remember for other, so y and z direction, they will use this workout, this value. We also produce something from x direction. So that's why from here, we can see sigma x will be equal to sigma x prime plus sigma double prime plus sigma x triple prime. So the prime that means from the different individual components, from normal stress, from the lateral stress, from y and z like this way. Of course, based on this, we can sum all the things together. Because if a tension, compression, it's the same to work out. So then, of course, we can get all of this value to the same way. Okay? So, of course, in the same way we work out for y direction and z direction, we also work out this thing, epsilon y and epsilon z. For all of these, we can work out. So that's why from here, epsilon x, epsilon y, and epsilon z from the 3D. So from the, let's say, this value, triaxial stress. So that's why from here, we can work out. And also for these 3 equations, we call generalized Hooke's law. Okay, so that's why I spent on 3 dimensions. So that's why this thing will be more complicated. But you can see this is quite a simple way. You can see epsilon x will equal to sigma x over E. So this is from the normal stress. But for the other two, so it will be minus V nu sigma y over E minus nu sigma z over E. Just use this proportional ratio work out. So that's why from here, we should know that's the way for the generalized Hooke's law. And they can work so complicated situation. Okay, whether these things happen on x direction, y direction, z direction, you can just put a value in. That's it. You can work out very easily. Of course, similar way can do the generalized Hooke's law for the shear stress. So of course, shear stress we can see from also lecture 1, the tau is equal to G times gamma. So that's the shear stress will be with some relation with the shear strain, but will be shear modulus. Okay, but remember, there's one way we must care about, because I put a comment here, under the shear stress, the material will change in shape, but will not change its volume. So we mentioned this one in lecture 1. Okay, so of course, based on this one, we can go the different shapes. So as well from here, we can work on gamma xy, gamma yz, gamma xz. That's so many complicated things. And then we can put all together. But remember, this value for the G is shear modulus could be related to the Young's modulus and the proportional ratio. Okay, this one just give you a little bit of idea. Okay, just these things. But we still go to the most situation for the normal stress, because eventually the one will change the dimensions. Okay, so for these things, we can get this idea for the one word called annotation. Okay, so that means the strain, normal strain will change the volume. Okay, so then of course this one we call volumetric strain. So that's me from 3D. Okay, it's caused only by normal strain rather by shear strain. So that's why for this situation will not applied. Okay, so that's why we still can get this idea. We can work on the shear strain in X, shear strain, normal strain in X, and normal strain on Y, normal strain on Z direction. So of course, based on this one, you will say this one for the small element, dx, dy, dz. So after the change, so you can see go to delta, okay, epsilon x, delta xy, delta z. So let's say 1 plus epsilon x, 1 plus epsilon y, 1 plus epsilon z. So for the all the dimension on the 3 or d. So times dx, dy, dz, and minus the initial one. Okay, so now of course we can get the value So delta V will be equal to epsilon x plus epsilon y plus epsilon z times delta x, delta y, delta z of these things, because they're very, very small for all these things. So now, of course, based on these things, we could say dilatation or volumetric strain will be delta V change in the volume divided by initial volume. So that means here we get epsilon x plus epsilon y plus epsilon z times dx dy dz divided by dx dy dz. So now we'll find here, so epsilon x plus epsilon y plus epsilon z. So then this one will go back to the previous equation. Put here epsilon x, epsilon y, epsilon z. Okay, that's from the generalized Hooke's law. We do everything. So of course, based on these things, we still can work out these things. For the E, okay, you still know that E will be equal to the 1 over 2 nu over E sigma x plus sigma y plus sigma z. That is called the dilatation here. We can get it. You can see only we work on the sigma x, sigma y, sigma z, and also Poisson ratio nu, and also Young's modulus. You see this is much simple for working. Okay, so from here we get this idea, so we can work on these things. But remember, there's some specific situation. Okay, this is called hydrostatic loading. So hydrostatic loading, that means all the x, y, z direction will be equal. Okay, forget us. We come to here, all the pressure will come to us equally. Okay, if not the pressure not equal, we'll be like this way, we'll go different directions. Okay, that's why they will call all the same directions of these things. So that's why for this situation, so sigma x, sigma y, sigma z will be all equal. So let's say will be equal to negative p, because it always will be compression. Okay, so that's why for here we can work out p over, we can put the value in the equation. So substitute a sigma x, sigma the negative p to the dilatation equation. Then we can work out, and then E is equal to 1 minus 2 nu over E times negative 3p. Then we can manipulate this equation, we can work on this thing. So let's be P over E is equal to negative E over 3 1 minus 2 nu. Remember, Young's modulus is constant. Nu is constant. That means this one will be constant. Clear? So that's will be easy for working. So of course, based on these things, that's why for here, we can work on these things. S1C called bulk modulus, or also called volume modulus over elasticity, but most we call bulk modulus. Okay, this is use K to replace. So that's why from here, we can get this value. So that's what put the value for most of the matters. Nu is equal to 1/3, and which means K will be roughly equal to E. So that means for the matters, the bulk modulus will almost equal to the Young's modulus. Okay, that's why you can follow an engineering handbook. We always say the Young's modulus are roughly equal to bulk modulus. Okay, so that's why here means this is similar way. But remember, even nu is equal to 0.5, that means here's no change of the volume when loaded. But this is for special material. So that's why for the high-tech knowledge, for different application, we will use different material to use. Some we use Poisson ratio will be negative Poisson ratio, okay, because we don't want to spend. It's better for space. We should care about, and also submarine. There's many situations they want some specialties. That's why we should get into all the things to understand the structures. Of course, the bulk modulus is a measure of the stiffness of material. So this material property provides an upper limit to Poisson ratio of nu equal to 0.5. But basically, most of the material, the Poisson ratio will be roughly 0.2 to 0.28 roughly. Okay, so of course this is one from the material, because the materials always will contain some flaws inside. There's nothing perfect. Okay, that's why for make these values smaller a little bit. Okay, we'll see one example here. So this one, a copper bar is subject to uniform loading along its edge, as shown here. If A, B, C, or A, B, T give to you A, B, that means the length, B is a width, and T is a thickness. Okay, so give the values before loading. So determine its new length, width, and the thickness after application of the load. Already give you the knowledge. The values, Young's model of copper is 120 gigapascals, and the portion ratio new copper is 0.34. Okay, that's why we can give the value. So we see the new length, width, and the thickness. Remember, so we want to get this value, we must get the idea from the original one we give to you, but we should work on the changes of this x, y, and z. So that's why we use the Hooke's law. So of course, general Hooke's law, epsilon x, epsilon y, epsilon z. So we can copy all these equations. Okay, that's why we can get this value here. Sigma x, 80 or 800 is 800 megapascal. So be careful of this because I saw someone try to put the wrong values from the given parameters. This is really okay. So you should know. So this one is not with the caution. Don't put the wrong values. Okay. So that's why from here it's 800 because for the mid-sem exam I found some student they put the wrong values because they give to you, for example, 100. They also put 1 or 10, not copy the right away values. Okay. And the sigma 1 will be in compression, okay? So 500 megapascal, but should be negative 500 megapascal. So remember, this is negative, okay? Tau xy, nothing here, 0. Okay, sigma z, also 0, okay? Because z direction, there's nothing there. So now, of course, based on this one, from generalized Hooke's law, epsilon x, epsilon y, epsilon z give to you. So now, of course, we can get all the things done. So as well from here, we can epsilon x, so sigma x over E minus new epsilon, sigma y over E minus new sigma z over A. Put the value here. So I prefer to get some less work. So let's put here negative new minus over A plus times sigma y plus sigma z. So put this value here, 800 divided by 120 gigapascal. So minus new 0.34 Johnson modulus, so 120 gigapascals. Sigma y, as we mentioned here, negative 500 megapascal. Sigma z is 0, so that's why from here plus 0. So that's why I can work out this value. Okay, so same way we can work out epsilon y. Same way we can work on epsilon z. Just put the values in. So put the equation, put the values in, and work correctly with your calculator. So this not joke is real because for the exam, some students everything right, but the final answer is wrong. So I believe you put some of the wrong values on your calculator. So before push the button for calculator or equal button, please check the values you put correctly. Okay, this every year put something like that. Also be the same time find something like this way. Okay, so that's why you should double check all the things, put the value here, and then you put this value. And that's why I highlighted different color to show you. Okay, so then later on we can work on the A prime, B prime, and T prime. So with this value, so 300 plus 300 times epsilon x, because we know from the lecture 1 we mentioned. So epsilon is equal to delta over L0. So that means that delta is equal to epsilon times L0. But this is change, but still plus L0. So that's why it's L is equal to L0 plus epsilon L0. So that's why I put these values. But remember, don't forget the signs. So that's mean here, There's a plus, the negative, 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 and put values here. So that's why from here we can get a new length, new width, new thickness. So just by using the generalized Hooke's law, you can get the values easily. Okay, that's all for the first part. Later on, we will go to the second part, where we have some break and come back. Okay, so welcome back. We'll continue our second part. Second part will be on the thin wall pressure versus. So basically, so this is very quite common. So if you just buy a train or drive your cars on the railway, sometimes you can on the road, you can see some very long truck. So especially for the petrol, okay. So a lot of things on the car, on the trucks. So that's most will be for the fuel, petrol inside, and also some will be gas lines. So there's a lot of gas for the bores. Depends on, but what they usually see the trucks with the long verses, but sometimes they can show the bores because this will be the liquid gas inside. Okay. So now, so based on this thing, there most is one name they call pressure versus. So they are closed structures containing liquids or gases under pressure. So because this pressure will be really high. So for example, tanks, pipes, and also pressurized cabins in aircraft and also space vehicles. For example, if we take flights, the flights also something like this. Okay, so there's a pressure. Otherwise, this see in the sky. So where's the air? There's no air. So that's because of the pressure inside. So of course, when pressure versus having walls thinner than their overall dimensions, they are known as a shear structure. For example, there's a lot of roof domes, airplane wings, submarine hulls, and so on for these things. But when do anything for design, this is very, very important because when to any design here, there must some stresses will be applied. Do you know for airplane wings, there's a lot of gas, not only get the petrol inside. Okay, for all the airplane, okay, they're stored in the airplane. Okay, so next time when you take flights, don't just go inside the first. When you just on the before go to the bridge inside the aircraft, you will see sometimes on just someone on the ground, they will fill petrol for airplane. They just put it in the hose like for your fill your cars. Okay, there's a hose go to the airplane. You will see they fill the petrol in the airplane wings inside. There was all the petrol was stored in the airplane craft. So for the wings. Okay, this is very, very common for you to realize these things. So of course, based on these things, so of course we should know there's a lot of stress were applied. So especially for cylindrical or spherical pressure versus, it's very common. But how much we should do design? You're gonna say, hey, I can put anything there, and then no, that's already fair. There's no use. So that's why we need some designs of these things. But how much we should design, especially for this very thin and also very huge components. You cannot go to anywhere. We do this one test. I do one test. No such kind of way. We must do these things before we can put it in the real components. That's why in the Motius one, I still remember I put one video from Boeing company to test the air wings. Okay, so that's why they know the strength because they will test the strength. So if you study bachelor here, so we didn't learn from Motius one, we did the mechanical testing. Okay, that's one of the way of mechanical testing for aircraft. You should do a lot of bending because in the plane, so in the sky they put many of this. But remember one thing. So for this kind of structure, it's very complicated. So we cannot say exactly, hey, how much we can work on? No. But for some specific situation, for example, if the inner radius to wall thickness ratio. So that's mean R over T is greater than 10. For this kind of what we call shear structure. So for this kind of situation, they predict the stress. So the only 4% smaller than the real values. So very, very close. Because we can use safety in factor, if you can remember, yeah? So that will be same for design. So as well for these things is very, very close. So if this one, R over T, is greater than 10, then of course, this value we will work out will be very, very close to the real situation. But when the R over T is less than 10, that value will be getting more and more errors. Okay, that's not accurate. So that means if we want to do some calculation of this thing, we must verify R over T is no less than 10 to guarantee your calculation is in the right way. Clear? Especially for exams, that's very important for you. Okay, I will mention it on. Okay. So that's why for these things, you can see a lot of things here. So you can see cylindrical versus, and also there's a lot of balls, gas tank. So this kind of called semi-spherical end. For this thing, but this all will be very, very like a ball. This thing is very common. Okay, if you go, so this is very common for see when for the on the truck, you can often see this thing. If you go to the old petrol station, you can see some kind of thing. Okay, but this thing is always for liquid. Okay, gas. Okay, LNG. Okay, so that's mostly will be used this way to do the store or the LNG inside. But why like this way? Why we want to put the design like this thing? Okay, why put it? Not just put it say okay, easy. Put the one scale and just put the end of these things. Why put this hemispherical for these things? That's because of the designs. Okay. For example, if you put a cylindrical pressure versa, so we consider these things as this thing, of course, with the wall thickness, inner radius R, and is subject to the inner gas pressure P inside. But how much for the design we can see. So if we can use the method of section, we can cut through. For example, we cut through here for anywhere. Of course, we can work out. There's two ways. One is on the hoop, just say circumference. Another one is longitudinal. One is this direction, and one is so this direction, as a cut through from this direction. Okay, one is this direction. So that's why it will be different. So for this direction, of course, this direction we call circumference. Conference. That means here is a circle. So this one is circle. That's why we cut through these things. We can see how much will be changed. So if we cut this thing, of course, we can see this one will cut off small thickness, so delta y, and then of course we know how much of the pressure will be. So the pressure we can work out. So summation all the fx will be equal to 0. That means 2, once 1 here, 1 here. Okay, the two sides. So 2 sigma y, so T dy, that's the area, this area. Okay, minus P times 2R dy. So that's why for this one, we can see there's a pressure. So that's why from here should equal to 0. Then work on sigma y is PR over T. Of course, sigma y is a stress, normal stress in the hoop or called circumference. Okay, that's why for this thing. Similarly, we can work on this direction. So like we'll cut through this direction. This direction, of course, we still can draw free body diagram. It can work out because there's a thickness T. So now, of course, we can say if it is R. So next summation O F Y with 0. So sigma 2 pi RT. That is the area around the thickness. And this one is the pressure is P inside. So pi R square. That means the whole area is equal to 0. Of course, sigma 2 is equal to PR over 2T. Sigma 2 is the normal stress on the longitudinal direction. So that means here on this direction of here. And the P is the inner gauge pressure. Remember, this we call gauge pressure because we use the gauge meter to measure because outside pressure, inside also pressure. But this one also based on the meter. Okay, that's why we can read off the values. That's why they can cancel each other for the atmosphere pressure. So that's why P is the gauge pressure, okay? So R is the radius, or inner radius of the cylinder, and the T is the thickness of the wall. But remember, you must verify. So R over T should be greater than 20, because as we mentioned before, only R over T greater than 10, so the error will be very, very limited or small. Okay, so that's why if this value is not met, it means you cannot use the equation as we did like this way. Clear? So that's why you must verify this step. So R over T is greater than 10 or no less than 10, okay, to meet the condition of using these equations. Of course, based on this one, we can see sigma 1 is greater than sigma 2, 2 times. So that's why for most situations will break like this way. So the break only circumferential or hoop, not on this direction, but on this direction. So on this direction, because this pressure will be 2 times of the longitudinal direction. Okay, that's a broken like this way. Clear? So this one we can get from the itself. You see, this calculation itself is quite simple, not that hard, because this simple way just work out. Draw free body diagram, you can work it very easily. Okay, so that's why from here just give you an idea how to. But sometimes we still see this kind of normal stress, sigma 1, sigma 2, we're also called membrane stresses. That's because of later on we can show later on why like this way. So if also like for the spherical pressure versus, you can see we still can, because still also for we cut on a halfway, so they can get this sigma 2 because of something like this. Clear? So that we still can work on here, summation all the Fy by 0. So sigma 2, 2 by RT minus P per square R, so it will be equal to 0. So sigma 2 will be equal to 2R over 2T. So that's why from here, this one, the pressure will be much, is half of this pressure. Okay? So that's why from here, so we can work on all the things because the sigma 1, sigma 2, or all the things here, because on the surface, the always, let's say, because the gauge pressure, that means here, the pressure will be equal to the atmosphere pressure, then gauge pressure will be equal to 0. Okay? So that's why from here we go to 0, then all the surface will be go to 0, go to normal to the surface. But still will be sigma 1, sigma 2, all the directions will be equally because of the circle. So that's why from here, they will go to all the direction will be equal to sigma 2. So for the spherical versus of these things. So of course, based on this one, so something like the soap balls. So the soap balls were something like this. So there's a soap ball film. So that's what we all with the same thing. We keep the same stuff, keep it like a ball, like the balls or bubbles. So because this one was membrane stresses. So if you learn from school level in physics, or you will learn fluid mechanics, okay, you will learn these things, but I will give you more complicated things. Just let you know, just called membrane stress, just let you know a little bit, something like a soap film, okay? So, but not hard for you to work out these things, just let you know something like this way, okay? So that's because of this. Then we should get an idea. So because there's all the pressure will be gauge pressure. So that's means based on the relative to the atmosphere pressure. Okay, that's why from here we can put anything. For example, if it's like a membrane stress, we can say it is a ball. Then you see all the x, y directions, and also there's also z direction. So of course, z direction will be go to pressure, so normal to the surface, but normal surface will be 0 on the surface. Okay, that's why from here we can see sigma 1, sigma 2 will be equal to PR over 2T for the outer surface, but sigma 3 is out of the normal surface, so it should be equal to 0. Remember, this is the gauge pressure, that's why it's 0. Clear? So that's why from here we can something like we can do this way. But remember one thing, but inside there's a pressure. Okay? Inside, because it will keep all the pressures. For example, you put the gas or liquid inside, there's definitely pressure, high pressure. We call pressure rise versus. So because of low pressure there. Okay? So from here, so of course, it's here inside. They still have a pressure inside. That means from surface 0 to inside P. So of course, there's some changes. The P, of course, in compression. So that means it's negative P. So that's why I put a comment here. Sigma 3 increases from 0 at the outer surface to a maxima of a negative P at the inner surface. Okay? So let's go from this kind of case. This is actual case. So when we design, that's we should get an idea. So let's say it's R over T is equal to 10, for example. Then sigma 1, sigma 2, you see R over T will be 10. That means sigma 1, sigma 2 should be no less than 5P. Clear? Everyone clear? R over T no less than 10. You just say 10, okay? So R over T 10 is a P times 10 divided by 2, that's a 5P. Clear? That means it's got 5 times higher than the maximum stress inside of these things. Okay, but we could further go the outward side. This will become smaller and smaller until 0. So of course, this value will much less compared to the sigma 1, sigma 2. Okay, so that's why for here we should know. So when they're more than 10, you will see that's much higher compared to the relative pressure inside. But this one, if it's small, then of course they're very close. Then we cannot ignore the influence of the pressure inside. But it's big enough, we can ignore the pressure. Clear? So that's why we should get this idea to let you know a little bit. Of course, we'll see one example. So the example here. So a cylinder pressure vessel has an inner diameter of 1.2 meters and a thickness of 12 millimeter. Determine the maximum internal pressure it can sustain so that neither its circumferential nor its longitudinal stress component exceeds 140 megapascal. Under the same conditions, what is the maximum internal pressure that a spherical vessel with a similar size can sustain? So as we compare, so for cylinder versus or use a spherical versus. So we should compare. How about these things? So that's why could be this, could be this. Okay, that's why we can see for the first one, we should verify because it is already designed whether it's useful for the thin wall versus or not. So that's why okay, R over T is a 0.6 divided by 0.012 because here in the diameter 1.2 meters and the thickness is 12 millimeters. Okay, we'll put the value here. So it's a 0.6. Remember, it's R, not D. Okay, because R is a 0.6 divided by thickness 0.012. So it's equal to 50, much more than 10. Clear? So that means the pressure vessel is a thin wall vessel. So that means we are happy and confident we can use the equation as we did by use of fluid body diagram. Clear? So then that's quite a simple way we can work out because we know for cylinder versus sigma is equal to P over 2T because you can draw fluid body diagram by yourself. You can draw that this way, okay? So that's why we can work on sigma 1. Sigma 1 is P over T. So then we can design for this. So because it's 140 megapascal, I will mention to you. Okay? So that's why from here, so we get 140 megapascal P over R over P times R over T. Then we can work on the pressure, should be 2.80 megapascal. So that means the pressure inside could be 2.8 megapascals. Okay? So of course, when this one is pressure reached, we still should longitudinal one, so sigma 2 is a half of this thing, so 70 megapascal, still suitable for the material. So that's why we are safe enough. So that's because sustain 2.8 megapascals. So that means from here, we can see the maximum stress in the radial direction, so sigma 3 max with P, is 2.8 megapascals. Okay, because this one is 50 times smaller than circumference one. So that's why here will be ignored. So that's why this one is much smaller, this thing. But remember, the value will be 2.8 megapascals. Okay, that's what sustained. So of course, we can still continue. We will use a spherical version. So let's see how much will the maximum value will be work. Again, so because this one will work out, this one is suitable for the thin word versus. So now we still can work use spherical with sigma 2 is PR over 2T. So this still can draw free body diagram. So for workout. Okay? So of course, based on this one, we can work out these things. So we can see there's a P sigma 2 PR over 2T, the 140 megapascals, P times R 0.6 divided by 2 times 0.012. We can see the P is a 5.6 megapascals. That's why for here, the spherical pressure versus will carry twice as much internal pressure as the cylindrical versus. So they can sustain high pressure. They say, hey, I didn't see much. I only see most for the cylinder versus. Okay, that's because the spherical versus is more difficult to fabricate. So that's why only for LNG company, so they use the balls because they can have a high pressure. Okay, because they use birds or something to transport. So that's why they can mostly can see use the spherical balls to carry LNGs. So that's why in the oceans, seas, they can see most with this shape, not with the cylinder. Cylinder only on the road you can see like this way. So that's because the cost will be different. And if they can sustain high pressure, so they can put more liquid gas inside. Now that's because of the economic. So everyone should consider this kind of for structure design. Clear? So that's why for these things we can get this idea for the operations inside. So that's the way we should consider many of these things. Okay. So remember, these things will be the topic so very important. So we can show this result to you. But remember, so we were in a tutorial question. So that tutorial question is very close to the standard final exam question. So that's why in the tutorial questions, I've given more details to work out. Okay. But basically the skills will be same way. We draw free body diagram, we work out, but we should verify whether this R over T is no less than 10 or not. If only on this situation, you can use to all the things use free body diagram. Okay? If not suitable, sorry, you cannot use because the error will be very huge. So that's why we should get this idea. So for exam, we cannot give you harder questions, but you must have the skills. Okay? Okay, so that's the basic thing of the knowledge. But later on, we should give you further things. So we get a lot of basic things on the different situation. So we already learn for normal stress, axial loading, and also bending, flexural stress, okay, shear formula. There's so many of this. But as we mentioned before, so it's a lot of things, not just for a single type of the loading situation. There's a lot that we combine together. Okay, so that's why I say structural member is usually subject to combined loadings. There could be a lot of things. So could be the internal axial force, shear force, bending, torsion, moment. So many things come together. But how can work together? Not just say, we just put it this, we just put this. No. So for these kind of things, we should also know. So in the industry design, of course, we should find where's the maximum. Okay, where's the minimum for design? So that's why for all the way we should find the critical points with the maximum bending, maximum shear stress, maximum normal stress. We should find always key to know the maximum values for different situations. But how can we work these things? So that's why we should combine all the things together. So for example, we should find the internal loading. Remember, mechanical solids, we solve problems of the internal stress and the internal strain and the relationship between each other because of the external loading. We mentioned this in the lecture. one. Okay, so that's why we should find the internal things. So for internal one, remember we must use a method of section. Method of section is a very basic thing for engineering mechanics and also for all the mechanics when we do the problem. That's what I mean to guys. For use a method of section, we must put this question in the mid exam and final exam. That's why please realize for final exam we still have such kind of thing. So if you lose the mark or didn't get a good result here, please strengthen this kind of stuff. This must question. Okay? So of course, based on this, we use the method of section, cut through any point of interest. And then we draw free body diagram, get equation of equilibrium to obtain the resultant forces, stresses, any other things put together. Okay? So of course, we should must follow the sign convention. So we should use sign convention to get the things. So remember, we must use a right-hand side view from the right-hand side. So you should know that's way positive, that's way positive value. So please follow these things, okay? So there's no way, don't ignore this because it's a basic thing. It's a sign convention. It's not only you like or don't like because industry, academia, computer software, all you follow the same thing. Okay, that's what everyone follow. You say, I don't like, doesn't matter like and don't like. Everyone follows the same thing. Okay? So of course, based on this, we should use free body diagram and work out equation of equilibrium. Of course, I found many students they didn't know how can draw free body diagram. But remember, free body diagram is a basic skill to solve problem of mechanics. Okay, so that's why if you don't know how to can draw free body diagram, I'm happy you come make a point with me. I'm happy you to how can draw free body diagram. Because it really is basic. If you don't draw free body diagram, I can't say you will fail or pass. I'm 100% sure you will fail this unit. Okay? So because free body diagram is a basic thing for you. So then on, we should know. So where's the neutral axis? So of course, we get a neutral axis. We should find the centroid of the cross section. So of course, these are also basic things you should work out. Also for engineering mechanics. Okay? So for these things, we have so many of this. Again, and again. So we did so many of these things. Then on, we should find all the things for the relationship for the normal stress, shear forces, and also the bending and other things. We should do these things. Okay? And of course, we should get all the equations to do all the work. But basically, so also only one thing. We say, hey, these are normal forces. But remember, the question will be much more complicated as you thought. So in the CR, sometimes have shear forces, and also have a bending moment. It will produce a lot of normal stress of these things. And also torsion, they also produce a lot of shear stresses. Okay, so of course, based on this thing, also come back for the thin wall pressure versus, you should also consider for all the pressure for cylinder or spherical motions from different directions because the structure will get cut for different things. Okay, so for all of these will come together. Then of course later on, we can use all the individual forces or other things. Then we use the superposition. So sum up. Remember, sum up, not just say the plus. Okay, you must consider the signs, whether it's a positive or negative. Remember, positive for tension, negative for compression, for stress. Okay, but for other things, there's also follow other things. For example, torsion, there's other ways. So that's why we should care about these things. Okay, so that's why for this thing, we'll always use the principle of superposition and put it all together. So then, of course, then later on, we can determine the results very easily. Same way, remember, so we put a lot of things. You see, in many lectures, we put, let's say, superposition. Okay, we can put a work on axial loading. We can put also torsion. We can also on the bending. We put it all together. Okay, so of course, these things could be solved problem simple and also complicated problem. But the industry, they would like to use these things, very, very useful. because the work individual, put together. Okay, so that's why we put all the things, consider all the things for axial loading, bending, transverse shear, torsion, put it all together. But remember, always remember the signs. So that I put you here's tension, compression, rotation. You should put yourself. Remember in the tutorial, I put use bracket. Wrong place say this is a compression, this is down, this is up or right or left. So keep the same thing for yourself. Okay, they say, yeah, I know I can do because I saw some students come to review exam papers. Oh, lecturer, I believe I know, but when come to exam, I feel I'm very stressed. I say, yes, that's what because I made to you guys. When you follow my way to do problem for tutorial, you say, yeah, I got it. But actually, when do the exams, you do everything by yourself. Clear? So that's why please practice the problem and do it by yourself. So put your time, find it out. I know if this instruction give you a lot of time, 1 day, 2 days, or 2 weeks, it will solve problem. But when put the time for the timely examination, so sorry, everyone's stressed. So that's why please, so do the work more ahead. So you just find it here because I found some students just found an exam paper. Oh God, I found somewhere in the book. I just turn all the pages on the book to find and just think, oh, how can I digest these things? It's too late because you have no time to come and study your textbook. Okay, so that's why please everyone follow the things. So position is quite a simple way. Okay, and then of course put these things and divide the loading into relevant component. Remember always put a positive or negative value. Give yourself sign. So remember this is clockwise or counterclockwise or something put together. Okay, not just yeah I know. You know, but you should show me evidence you know. Okay, so to make yourself okay, I get this project, I done. I get this question, I done. I get a full mark. So not just I try this thing, I try no. That's why in the exam, please use a few minutes. Quick read through the question. Find which one is easy, which one is hard. Do the easiest question first. Don't do the hard question. Oh, this question is so hard. This question is so hard. You just say 100 times so hard. Didn't make any sense. Will not help you. Will make yourself frustrated. Okay? Do the easiest question. So you will get, oh, let's get it. Yeah, I believe I got this mark. I just count how many marks I will get it very easily. So that's why you get more and more confidence. Okay? Not necessarily question one is easy for you, or question some is later is hard to you. No. Some you good in this, some good in that. So that's why from the easy question, do it. Get a mark. Then put the hard question in the end. Okay? So that's where you get good results. So of course, that's what comes to here. You still should make yourself clear is a positive or negative, especially put it, for example, in tension or compression. This side, tension. That side, compression. When tension, compression, of course, they will put something different. So that's why you should use that something to lock your head. Hey, this is positive, this is negative. We sum up together. So 1 plus 1, 2. 1 plus negative 1, 0. Just question, the answer is quite a lot different. Okay, so that's why this is very important for you to realize. We use algebraic adding or summing the results to let you know, because we have so many such kind of practice in the tutorial question and also lecture example. Okay, so keep yourself understand whether it's up or down or left or right hand or tension compression. Just keep yourself. You write down this thing for yourself. Okay, and also we can use sometimes we use relationship. If you can still remember, we use the axial loading, any other thing. This is always the same method, but just equation of the relationship of loading and strain use different situation, because normal stress, bending, torsion, the equation will be different, but the logics, idea will be the same. Okay, so now of course we'll put all the things together. So checklist one is working, a lot of working, but we should pay special attention to the indeterminate structure. So indeterminate structure is most widely in the engineering problem. Okay, that's why we should care about this. For example, for mid-sem question 2, is for the you should not determine whether it's an indeterminate structure or not. Okay, that's why you should get this idea, whether touch or not touch. So that's the first step. That question actually from the practical problem. Okay, so that's why please understand this kind of work. So of course, all the things will come together. So I believe you're familiar with this thing. This is from the tutorial from lecture 4, I think lecture 4, lecture 6, I think lecture 4. Okay, so this one you can see this kind of structure will be could be a lot of different type of these structures. So of course we can work all the things sum up all together. So now of course based on these things we can put several different type of loading simultaneously. But remember, because we can divide them in individual, but they all put together. So now of course we can get the things. So where's the maximum stresses? So of course we put all together, and for these things we should use design, but we still consider the safety factor for the safety design. Okay, so from these things you can see they get a lot of structures from these things, but then we can see we can work out these things. So of course these things we should consider so many of these. You see we put anything here, we can get a shear force diagram for this. We can find out where's the maximum. Where's the maximum? Of course, you can see that area will be maximum for the things. Okay, so of course somewhere below. So that's why we say care about where we will use for design. Okay, so of course we can use a transverse shear stress, average shear stress, and of course we can also get a moment. Moment also have a fractional normal stress. We can get also normal stress. We see use the maximum value here. Okay, and then of course based on this thing we can also work on the values or the torsions. We can go all the things together. But remember, for the shear force diagram and the bending moment diagram, as I mentioned, this is very, very important for designs because they can give you an idea. For many, many big companies, they're always on the big screen on the wall, just show where's maximum, where's minimum. They can see such kind of things. Even for transportation department, it also monitor all the cars on roads. They also have pictures and the monitors. But also water corporation also like this way. So that's why for this, you will find the way to monitor where's the maximum, where's the minimum, and this will be found out. The maximum place most will be big issues. That's why they pay special attention on that specific spot for these things. So now, of course, we see one example to show you how can see. So this one, yeah, that's simple because we did a lot of things. This is only compression. Not really. Because if you can remember, for all the things we learn will be on the centroid or neutral axis for the loading. But this is not. This is just loaded on this way. Because, for example, I put here, I put every load, you can see the change. Yeah? So a lot of just compression. Put it here, the compression. You can see the move. But when we put it here, they rotate. So that's why from here, same way for here. You see, a force of 300 kilonewtons is applied to the edge of the member shown in the figure A. So regulate the weight of the member and determine the state of stress at the point B and the point C. Look here. If this one, the load is in the center, that's easy, yeah? Because just one compression, that's it, done. But because this one is on the edge, no other way, because this will make different things happen because we apply one bending moment on the parts. So from here, so we can get this idea. So the BC will cut on the BC, okay? Because BC is an interest of location. So we cut at BC. So of course, based on this thing, we can draw free body diagram. We can say all the summation of the force will be 0. Remember, this one still the normal stress compression. So of course, this is also the compression. So go up. So that's mean here will be 300. So I didn't use the equation, just let you know of these things, okay? So of course, here with 300 kilonewtons up, will also compression for here. Again, because this will apply on the edge, this is not on the centroid. So of course, this will also apply one bending moment. So that's why summation of all the moment will be equal to 0. So now, of course, from here, how much will be here? Because the center, so this are about 150 millimeter away. So of course here, so 150 millimeter, the 0.15 times 300 kilonewton. So that's be 45 kilonewton meter. So about the centroid. Clear? So that's why we bring a moment. So that's why from here, there's a moment we also for our centroid, but it's from this direction. So because this one we put one compression, it's also put one compression for that side. So now of course we know there's a normal stress compression and also apply for bending moment. So that's why we can see get a normal stress sigma is equal to n over a. We can work out. So this is in compression. That's why I put here comments. You have to put 70 to remember it's compression. Okay, so that's why here is a 10 megapascal in compression. But same way, because this one will be put a moment. Moment, as we say, this one where moment will also flexure normal stress. So flexure formula. This one for the moment here will be applied the compression. In bottom one will be applied for tension. Okay, as well from here we get the idea. This one will also have this loading. So sigma max was equal to mc over r. C is from the centroid to the farthest away. If you still remember, okay. So that's why from mc over r. So of course you can get this idea because of the cube. Still you can remember r is 1 over 12 bh cubic. So m, which is work at c is farthest away. This is say is 150 millimeters. So that's why from C and B, C of course in compression, B will be in tension. Okay, that's why from here we can work out. So that's why from here, sigma max, MC over I, we can work out it's a 30 megapascal. So that's why we mentioned these things in lecture 6. Hope you still remember this thing, okay? So of course, based on these things, C and B point will have a different normal stress from the bending moment. So that's why from here, sigma B, everyone can remember? Sigma B here, because of the compression, of course it's compression, but because it's a molding moment, this is why we're in tension, okay, for the flexure formula. That's why here, sigma B, remember, put it here, negative N over A because it's a compression, plus MC over R because this is tension. So that's why it's a negative 10 plus 30, so it's a 20 megapascal, but in tension. It's reasonable because in the below the neutral axis in tension. But how about C? C point, so of course C point here, still compression, but there's a bending moment here, that's why here will be in compression. So that's why this one will be negative NA, is a compression, plus negative MC over I, also compression. So that's why here negative 10 plus negative 30. So that's a negative 40 megapascal. That means in compression. So you see, only the load just a little bit shift the location. Of course, this one will produce combined loading. So that's why for real problems, it's much more complicated. For example, if I push this disk, this one, if this one enough, this one not try to move this way, this still will rotate. Okay, because I didn't put this thing in a neutral axis. So that's why here, for the similar way, is still combined loading conditions. Okay, so hope you guys can get this point. But we should find where's the neutral axis for this 0 point. So of course, this is linear, of course, we can find use the similarity of two triangles. We can work out. I will not mention this thing because we did this one in a relevant lecture before. Okay, so that's the knowledge for these things, for the combined knowledge. So that's why for these things, we can find for the industry, just for the small things, you can see there's much more complex. But the next lecture, we'll give you more, for the first part, we still give you some whole, they put all the things together, go to industry. Okay, but the second part, we'll put something for the unit review of these things. I'll give you some hints further of these things. Okay, that's all for this, and also some extra questions to let you know a little bit. I will not put these things because because of a little bit angle, so that's why we put a little bit complex things. If you're interested, you can practice. If not interested, you can do it. Okay? So that's all for this part. So hopefully you can get some idea of these things. But remember one thing, this is almost conclude this unit. So that's why for the topic. But if you put any sum all together, you'll find, oh my God, it's so hard because combine all the things together. But that's the real problem for industry. Okay? So for you, I said from the first I mentioned to you, I fully understand you're a student. I will not give you hard question for the exams. Just give a simple way so you understand the topic by topic by topic. So that's the way for you. Okay? Thank you very much. So then we'll have a break and then we'll come back for the tutorial questions. But remember, tutorial questions are very, very, very related to the final exam. Please pay attention for these things. Okay? Okay, thank you.